We are going to learn about electrochemistry for the next week or two in this class. And so be following along if you're watching the video too. This is the Chapter 3 guided notes. And be following along. There's quite a bit of information that I want you to write down as we go through these slides. So please have your guided notes out and ready to go. So first of all, electrochemistry. Let's start here. It's the use of redox reactions. Guys, have we studied redox reactions? Yeah, and hopefully we know a lot at this point about redox reactions. But electrochemistry is the use of redox reactions to change chemical energy into electrical energy, and vice versa. So we did a lab last class period where you built an electrochemical cell and you took chemicals and you converted it into what, guys? Electrical energy. And we measured that electrical energy in the terms of what? Volts. And so we have done this. That's what electrochemistry is. But did you know that we can also take electrical energy and then convert it back into chemical energy? We're going to do a lab on that coming up in the course. Okay, electrochemical cell. This is what you built last class period. It's an apparatus that allows a redox reaction to occur by transferring electrons through an external converter or connector called a wire. So we're transferring electrons through a wire. When we do those redox reactions, we can actually use those electrons to do something for us. They do work for us. And we send them through a wire. And then we send it to a buzzer, right? You made the buzzer sound? Or we send it to the LED light and you made the light come on? Well, there's two types of electrochemical cells. Number one is a voltaic cell. Okay, a voltaic cell is also called in some chemistry textbooks a galvanic cell. So these words here mean the same thing. Voltaic and galvanic. I will usually call it a voltaic cell because that's what I prefer. But just be aware that a galvanic cell is the same thing. And there's an electrolytic cell. The one that we built last class period was called a voltaic cell. How I remember it is because did we produce volts with ours? Yeah, if you produce volts from it, it's called a voltaic cell. And that for me was pretty easy to remember as I was learning this stuff. Okay, so electrochemical cells are either voltaic or electrolytic. What's the difference? Let's quickly go over the difference. A voltaic cell, which is what you guys made last class period, changes chemical energy into electrical energy. And we measure that electrical energy in terms of volts. So if it produces volts, it's called a voltaic cell. Well, the other electrochemical cell is called an electrolytic cell. And they do the opposite of voltaic cells. They change electrical energy into chemical energy. So they're just the reverse of each other, just the opposite of each other. We are going to make an electrolytic cell in the lab in a couple weeks. For this lesson, we're going to look at voltaic cells first, and then we're going to look at electrolytic cells. So let's go back to what a voltaic cell is, exactly what you built in lab last class period. Here is an example of a voltaic cell. Okay? Again, it produces volts. Voltaic cells are spontaneous. We're going to see this word a lot coming up. What does spontaneous mean, guys? If it's spontaneous, do you think it happens on its own? Or does it need help? Yeah, it happens on its own. If you'll make that note, happens on its own. Okay, that's what spontaneous means. So voltaic cells are spontaneous oxidation-reduction reactions where electrons are transferred and energy is released. So I showed you this exact demonstration in class. This is a zinc strip. Remember when I put that shiny piece of zinc in this copper sulfate solution? And within seconds, it started to turn black. in kind of this rust color. What was that stuff forming at the bottom? That was copper, pure copper. Well, how did we get pure copper from copper sulfate? Well, what happened was that 2 electrons came off of this zinc strip and joined the copper plus 2 ions that were in solution. And when you add 2 electrons to this, don't you form copper with an oxidation number of 0? Pure copper is forming and it's coating this zinc strip and actually falling off, and we've built a lot of copper at the bottom. That's an example of a voltaic cell. But are we using these electrons to do work for us in this example? No. I mean, they're reducing the copper, but we're not using those electrons. So what you'll see most times with a voltaic cell is something that looks like this. Okay? They've set up their voltaic cell so that they have a wire, and we can capture these electrons, these flowing electrons, as it goes from the zinc to the copper. And like we did in lab, we made the buzzer sound, or we made a light turn on. We can use those electrons to do work for us. Voltaic cell uses electrons produced from redox reactions to do work. Okay? So voltaic cell, we use those electrons to do work for us. Here's a typical voltaic cell. You've got a zinc strip. So zinc, pure zinc, right here. You've got some copper sulfate. That's the electrolyte solution that surrounds the copper strip. Whoops. So there's my copper sulfate. You've got zinc sulfate. This is the electrolyte solution that surrounds the zinc strip. And then we've got a copper strip. Okay? And so that's what a typical voltaic cell will look like. And then let's point out a couple more things. A salt bridge. Okay, we're going to talk a lot about a salt bridge. Ours that we did in lab didn't have a salt bridge. What did we use that was equivalent to it? What was our salt bridge? The porous cup, exactly. So, but it served the same purpose. So there's some terminology to know, and you've got some things to write down in your guided notes right here. Reduction, hopefully you know this by now, is the gain of electrons. So reduction is the gaining of electrons. Number 2, oxidation is the loss of electrons. What mnemonic did we use to help us remember this? Oil rig. So I want you to write that here. If you ever get confused, think about an oil rig, which the O is for oxidation is loss of electrons. Reduction is gaining of electrons. Okay, there's some other terms to know, like this one, electrode. An electrode is a piece of metal where either oxidation or reduction occurs. So it's just a piece of metal where either oxidation or reduction occurs. There's 2 electrodes in an electrochemical cell or a battery. There's two electrodes. One is called the anode. The anode is the electrode where oxidation occurs. So oxidation occurs at the anode. The other electrode is called the cathode, and it's where reduction occurs. So when I was learning this, I learned it this way, because that's kind of hard for me to remember. Oxidation happens at the anode, reduction happens at the cathode. This is what I learned to help me remember, and I think it will help you as well. Think of a red cat. Okay? It's kind of a mnemonic to help us remember that reduction happens where? At the cathode. So red cat. Always think about a red cat. That means reduction happens at the cathode. And then from process of elimination, we know that oxidation would then occur at the anode. So red cat. Okay, there's a salt bridge. We've talked extensively about a salt bridge. It allows ions to flow through and keep our electrochemical cell neutral instead of building up a charge. But what's important to remember is that cations flow toward where? The cathode. That's why it's called the cathode, is because cations flow toward it. And anions they flow toward the anode. Again, that's why it's called the anode, because anions flow toward it. And then finally, electron flow. Which way do electrons move? The electrons always flow to the cathode. So electrons will go to the cathode. Let's make a little note in your notes as well. The cathode is the positive side of the electrochemical cell, and the anode is the negative side. And that's kind of easy to remember because cations are positive, and that's what cations are flowing toward it. Anions are negative, and anions flow toward the anode. So I think it's kind of easy to remember that. Okay. For this chapter, by the end of this chapter, I expect you to do a lot of things, but one of them is to be able to diagram a voltaic cell. So in the next few slides, we're going to learn how to diagram this electrochemical cell. We're going to learn it with zinc, the zinc strip, and a copper strip. That's exactly the metals that we use, or the electrodes that we used in our lab. So it should be familiar. But anyway, we're going to go through it. Before we start, this voltmeter here is reading 1.1 volts. Does that seem familiar to you guys? That's exactly what yours produced, right? Yeah. About 1.1 volts. And because we made the same one in lab. So let's go through it. A typical cell looks like this. Oxidation occurs at the anode. Zinc was our anode. This was the negative side of our electrochemical cell. And reduction, whoops, let me go back. And reduction happened at the cathode. So copper was our cathode, and this is the positive side. How do we remember that reduction happens at the cathode? The red cat, reduction happens at the cathode. Okay, so our anode was zinc, our cathode was copper. Well, once even one electron flows from the anode toward the cathode, the charge in each beaker would not be balanced and the flow of electrons would stop. Here's what this slide means. Zinc is losing electrons. It's being oxidized. So this electron comes through the wire, and if the electron comes over here to the cathode, wouldn't this build up a negative charge if this was allowed to continue? Wouldn't it build up a negative charge if electrons flow toward it, guys? Yeah. Well, do electrons like to be by a negative charge? No, because electrons are negative. Remember, electrons are this particle that's negative. Would they want to move to a side that's negative? No. So your electrochemical cell would stop working. So how do we balance the charges here? A salt bridge. Okay, so let's go talk about a salt bridge. It says, therefore, a salt bridge, usually U-shaped tube. So here's the salt bridge in this cell. We used a porous cup, so ours was a little bit different, but the same principles apply. It contains a salt, so it's got these cations and anions, and it allows for the transfer of charge. What flows toward the cathode, guys? What flows toward the cathode? Cations. So there's this movement of positive charges toward the cathode, and what flows towards the anode? Anions. So there's this flow of negative charges toward the anion. So these positive ions, these cations, are coming through and they're balancing out the charges of these electrons that are coming to the cathode. And so that way we keep a neutral charge in our cell and the flow of electrons can continue. Okay. So in the cell then, electrons leave the anode and flow through the wire toward the cathode. So here's what's happening. Our zinc strip here is losing 2 electrons. And those electrons are flowing over here. So these 2 electrons come onto this copper strip. As the electrons leave the anode, though, the electrons the cations formed, dissolved into the solution and the anode in the anode compartment. So here's what's happening. As the zinc loses 2 electrons, so 2 electrons leave, these zinc atoms are now falling off into solution as zinc plus 2. Because they've lost 2 electrons, now becomes a cation zinc plus 2 charge. So they fall off into the solution, it becomes part of the zinc sulfate. Okay, so you lose 2 electrons here. Now the zinc atom, which is now a zinc plus 2, will come off of the zinc strip. Well, as the electrons reach the cathode, cations in the cathode are attracted to the now negative cathode. So these 2 electrons will come down onto our cathode strip, this copper strip, and now this Cu plus 2 that was in our copper sulfate here, these 2 electrons will now meet up. This cation here will now meet up with these 2 electrons, and it forms copper with a oxidation number of 0. So you're forming pure copper now, and what that does is it adds to this copper strip. Is going to get bigger over time because now you're pulling the copper ions out of the solution and it's forming pure copper on this copper strip. And what's happening to your zinc strip? Well, it's getting smaller over time because remember they're falling off and the zinc plus 2 ions come into the water, into the solution here. Copper is being built up, and so you'll see the copper strip is going to grow over time. The zinc strip is being corroded, or it's being dissolved. Okay, so the electrons are then taken by the cation, and the neutral metal is deposited onto the cathode. So this neutral copper is then deposited onto the strip, making it bigger. Okay, so hopefully that helps you diagram an electrochemical cell. Practice problem 17 is something that I'm going to put on the test. So I would expect that you know at least this much information. So let's go through it. It says to diagram the electrochemical cell shown below with the following terms. I want you to put where copper is, where zinc is. Let me help you get started. Let's just call this one zinc. It doesn't really matter. And this one copper. Okay, so I did the first 2 for you. But I also want you to tell me where the salt bridge is, the cathode, the anode, the copper sulfate, the zinc sulfate, the electron flow, cation flow, and anion flow. So please try that now. If you're watching the video, please hit pause. See if you can diagram this cell. Once you have your answer, hit play and see if you got it right. Okay, so let's see how you did in diagramming this cell. So let's just go in order. Guys, where's the salt bridge? Isn't it this structure right here? Yeah, let's put salt bridge. It's my salt bridge right there. Where's my cathode, guys?
It's the copper.
The copper was our cathode. So I'm going to put cathode here. Now cathode is positive, so I'm just going to put a positive sign there. The anode then would be the what? The zinc. And that's the negative side of our cell, so I'm going to put a negative sign there. Where would the copper sulfate be? Isn't that surrounding the copper? This is the electrolyte solution that is surrounding the copper strip. Okay, the zinc sulfate will be our electrolyte solution that's surrounding the zinc strip. So zinc sulfate goes there. Which way is electrons going to move? Toward which side? Toward the cathode. So I want you to draw in your arrows like this through the wire and put electron flow. So electrons will always move toward the cathode. They always move toward the cathode. Okay, so we've got electron flow. Now let's do a couple more. We've got cation flow. Which way will the cations move? Toward the cathode. Yeah, that's right. So I want you to draw an arrow. Your salt bridge is what's going to take these cations. So the cations, which are positive, move toward the cathode. That's what makes it the positive terminal, or the positive electrode. And the anion flow is going to be which way? Well, it's going to be toward the anode. The anions, which are negative, flow toward the anode. Okay. And so hopefully that makes sense. Let me review this one more time. If you have 2 electrons flowing through the wire, won't that build up a negative charge on this side of the cell? It would. So to balance that and to keep those electrons flowing, cations are being moved through the salt bridge toward the cathode. So that keeps our charges neutral so that we can keep this flow of electrons going. Otherwise, a negative charge would build up here, and the electrons don't like to be by a negative charge, so the flow of electrons would stop. Okay, hopefully that helps us. We built one in lab. We've now diagrammed them and explained them through the notes. I hope that this is helpful in diagramming electrochemical cells.